God doesn't play dice. Einstein, stop telling God what he should do with his dice. Imagine a huge forest with no one in it. In that forest a tree falls. And here's the question. Will there be a sound of a falling tree if there is no one to hear the sound? Yeah. That's a stupid question. Of course there's a sound. What's the question? But the question is how to prove there was a sound. Well, let's leave the forest alone and start with the trivial. Everybody loves a cat, so we have an imaginary cat. We put it in a box with poison in it and close the box. Yes, this is Schrodinger's great mental experiment, and here's the point of it. While the box is closed, we don't know if the cat is alive or dead, just like we don't know if has eaten the poison or not. So our cat is in two quantum states at the same time. And to determine the state of our cat we need to open the box, that is to make an observation. Skeptics will say that it is nonsense and the state of our cat does not change from that. We will open a box and everything has already happened, just we do not know it yet. But this objection works only with an ordinary cat, and our cat is quantum and exists according to laws of quantum world, and their everything is not so simple. Today I want to tell you about a confrontation between two of humanity's greatest minds, actors. Niels Bohr, Albert Einstein, an unsuspecting cat, and a god who gets in the way of a dice game. Albert Einstein, theoretical physicist, one of the founders of modern theoretical physics, winner of the Nobel Prize in Physics in 1921. Einstein is best known, of course, for the theory of relativity, but only a small part of his merits. Niels Henrik David Bohr, Danish theoretical physicist, one of the creators of quantum mechanics. He won the Nobel Prize in Physics in 1922 for his contributions to nuclear reactions, known as the creator of the first quantum theory of the atom and an active participant in the development of the foundations of quantum mechanics. Well, with the cat and God, you're all familiar. Let's designate the subject of the dispute and then we will analyze in detail each of the theories. That once and for all to understand this issue. In fact, the question is the reality of the universe, of course. I do not mean whether the universe exists in principle, although there are interesting theories on this issue. Bohr and Einstein were good friends and engaged in many physics-related conversations over the decades. One of these, held in 1927, is now known as the Bohr-Einstein debate. They argued for different views regarding the observation that the electron behaves as a particle in some experiments and as a wave in others. Bohr theorized a concept that could explain the phenomenon. He said that something could be two phenomena at the same time, though we could only observe one of them. In this way, the fundamental principles of quantum mechanics were established. Bohr also pointed out that the fact that a particle is observed is what makes it exist, which later became known as the Copenhagen interpretation. Einstein, on the other hand, argued that particles exist whether we observe them or not. And so, have you seen the movie Ant-Man? Remember why you can't fall into the quantum world? Yes, because everything works wrong there. Let me tell you exactly what works wrong. Look now at the desk in your room, and imagine that it only stands there when you see it at other times. When there is no observation of the desk and the door is closed, your desk simultaneously falls into a black hole, stands at your neighbor's, or just disappears in an unknown direction. Sounds like nonsense, right? But that's how elementary particles behave, and it's a proven fact. Back to Albert Einstein. He was a serious guy, and he didn't accept the fact that a table could go missing when it wasn't under observation. Einstein absolutely did not accept the concept that the observer somehow influences the event, saying that the moon still exists even if we are not looking at it. Nothing's made any sense yet, has it? So let's dive into the hard physics. There's this thing called the uncertainty principle. Also known as the Heisenberg uncertainty principle, is a fundamental concept in quantum mechanics. It states that there is a limit to the precision with which certain pairs of physical properties, such as position and momentum, can be known simultaneously. In other words, the more precisely one property is measured, the less precisely the other property can be known. And there is such a thing as an observer. And in quantum mechanics, the very fact of observation affects the result of measurement. The problem is that the particle in its initial form can have rotation in both directions, fly into directions, and in general is simultaneously into places, and this is its normal state. But everything changes when a curious scientist intervenes and puts his hands on it. At the moment of observation, its direction, speed of motion, and location are determined and actually appear. This effect is called the principle of superposition, and it was this fact that Albert Einstein could not recognize. Now, let's talk about Niels Bohr. He's actually the father of modern quantum mechanics, and he was just fine with the uncertainty principle and particle superposition, and his numerous studies showed the validity of these theories in practice. The whole point of quantum mechanics is based on uncertainty and probability calculations. That is, the trailer is either a gobbledygook or a puffball, or we know the momentum of the electron or where it is. But that's still under the woes of further emerges the concept of quantum entanglement. Let me explain in a nutshell what it is. Imagine that you find a shoe in the dark, and when you try it on you realize that it is right. It is by realizing that it is right that you know exactly that the second shoe somewhere in the dark is left, and moreover it is exactly left, and even if you turn on the light and make all the necessary measurements, it will be exactly 100% left. Now imagine that you received a package from Alpha Centauri, and when you open the box you realize that it contains a right shoe. So the sender kept the left shoe. That makes sense so far, right? Everything seemed logical to Einstein, and he said that the property of particles is predetermined and the observer only receives information that has long been a fact before the observation began. So the shoe is always right and always left, and nothing changes. But Bohr believed that it was the observer who formed the property of the particle, and so the shoe of your hands became left only at the moment you opened the box. And so the other one acquired the property of left at the same moment. So there's some way of transmitting information faster than the speed of light. It's impossible, you'll say, and you'd be right. But everything I've told you above is an experimentally proven fact. The experiments showed that the mathematical basis of quantum mechanics was correct, and that was the key breakthrough. And so if you summarize everything I've said above, you'll understand what was so confusing to Einstein at the time. Quantum mechanics was a young science that was inexorably shattering the whole idea of how the world worked. Bohr in turn was a pioneer in the world of physics. He was the first to describe an amazing property of the electron, which in recent times has been called the quantum jump. It consists in the fact that the electron can move only along a certain orbit and can jump from orbit to orbit without spilling the distance between orbits. That is, it simply disappears in one meteor and at the same moment appears in another. Later, the legendary Jungian experience showed that photons can behave as a particle and as a wave at the same time, but this is impossible. Yes, I in this clip constantly say the phrase "it is impossible." Scientists later realized that, in fact, the wave effect is not due to there being more electrons, but where the electron is more likely to be located. Quite simply, it's impossible to know exactly where an electron will be and to calculate its trajectory. You can only point your finger and say, if I look here, what is the probability that there will be an electron there? It was the fact that quantum mechanics is all built on uncertainty and probabilities that so confused Einstein, who in turn was sure that quantum mechanics was simply not accurate and not fully understood. I think it was Einstein's constant challenging questions that allowed the scientific adherence of quantum mechanics to prove its validity so quickly. As time went on, more and more quantum mechanics equations describing probabilities appeared, and with them, more and more calculations were made that showed the amazing accuracy of probability calculations. When we talk about probabilities, an old joke comes to mind. What's the probability of meeting a dinosaur in the street? Well, 50-50. It's that I'll either meet one or I won't. But to make you realize how accurately the equations of quantum mechanics predict probabilities, I will tell you that lasers, transistors, and even high-speed internet, which you are now using, also work on the basis of these equations. In the greatest controversy of the 20th century, Niels Bohr won. Albert Einstein never recognized quantum mechanics until his death. As science proves to us, God does play dice. Despite their differences of opinion on quantum mechanics, Bohr and Einstein had a mutual admiration for each other to the end of their lives.